Welcome back. We're going to try to wrap up our journey into implication by looking at two further types of implication and the logic that you'll need for them. This one will be based on process and incident, or what technical words are intuitionistic and classical logic. These are foundational for planning purposes primarily. This is where you simply care that things happen and that you can explain them to others, but you don't get into the nitty-gritty details of, for example, how many resources are needed. We've covered that in a separate video. So to get started, let's see what we have in the process camp. What I will mean by process is that I care about how things work, but not so much how many things are needed to set it up. For example, I don't care if there are 5 eggs or 1 egg in a recipe. I just need eggs. Eggs are an ingredient. They're giving me a process, but I don't care about the mechanics of that process. So it's a little bit simpler than the raw instruction manual, but not completely devoid of meaning either. So what we'll need to keep track of here is that the premise exists, but we won't necessarily need to know how many times the premise exists. This is ideal, for example, in mathematical settings. If I was to say x is greater than or equal to 2, I only need to tell you that once. Once you know it's true, it's always true, and you can use that fact as many times as you like. It's not a perishable resource. So let's see how we might use a resource-free rule. And we need to add this to our logic. Remember, our logic is trying to not put in things that aren't true of every single situation. Each context is allowed to pick the rules that it needs. So we have to tell our logic how to have these rules. The first rule is called weakening. The weakening rule, without context written in here, but if you like, you could add context to both of these. The weakening rule says that you can feel free to add things that aren't being used. So if I have that A entails B, so I have a premise A, which leads to B, then I could also add a further premise C and still entail B. This isn't going to be true in, for example, too many cooks in a kitchen, right? If you're scheduling things and you have enough jobs for 3 people and a 4th person shows up, you don't have enough jobs for 4 people. If you have a cake that has 4 slices and a 5th person shows up, 1 person doesn't get cake. So we don't want to take this rule to be true of every type of logic, but it's certainly true of, say, if x is greater than or equal to, you could also add that x is greater than or equal to 7. X is greater than or equal to 0. So one could follow from the other or be completely independent. If you're not using it, it doesn't matter to the mathematical logic. So weakening is a good rule to add in some situations, and what it lets us do in terms of implication is that we can reuse one premise to get as many forms of the premise as we like. So if we have some argument that depends on reusing P, we're allowed to reuse it under weakening. A logic with weakening doesn't care about how many times P shows up. But that's only going in one direction. We should also like to come down. If we have too many resources repeated, maybe we don't need to keep repeating ourselves. And so that's this next rule called contraction. If I repeat the same premise more than once, I can write that with a single one. Notice there's a slight generalization. Over here, I used C. I could add to the weakening, I could add any premise different from A. With contraction, I only remove a copy of one of them. So I always keep at least the premises that I had there. If I had A comma C equals B, I wouldn't necessarily be able to get rid of C because it could be that both of those together give me B. So this is true for facts, but false for resources. If you have 1 egg, that's not the same as having 2 eggs. So we wouldn't call these equivalent. With implication, what this does is that we can simplify a long list of premises to a short list of premises, and that's the information we would want. So what does this give us? It gives us an implication that's known as intuitionistic implication. This is where we use the same grammar of if then else or an arrow. We entail it now with just a single premise, and that could in fact stand for many premises. And that gives us a P implies Q. It's nice and tidy. When we're doing something like linear logic, we have to count how many times we're using the resource. The elimination rule can similarly be tidy. It looks like the standard modus ponens. P implies Q, and if you're given P, then you get Q. This actually could, in the presence of weakening and contraction, have represented multiple passes at P, but you're allowed to use them as many times as you like. So in many mathematical arguments, part of the implicit context is that you're allowed to weaken and contract, reuse the statement as many times as you want. But switch to a programming language where you have shared resources in a database, or you have a file that can only be used one person at a time, and all of a sudden you'll want to switch to a logic that is not intuitionistic because it doesn't have the fine-grained details of how accessing that premise needs to share. So keep these in mind, and now let's move to the weakest of all possible implications, known as classical implication. So here we care about the incidents only, what happens, not how it happens or anything else. So in an incidence system, we simply want to write down that we know one thing leads to another, process irrelevant, and we certainly don't care about the timing or resources that are used. We're simply replacing the actual statements, the sequence, the P's and Q's, with their value, their judgments. Are they true or are they false? And this gives a very simple version of an implication, which is easy to memorize and is the most common form of implication taught in most sciences, even though it doesn't quite meet the needs of computation. But keep this one in your back pocket. Here's the general rule for classical implication. You only need to remember one rule: never allow true, then false. If you keep that in mind, that's the one illogical practice. Now, we saw before there's other properties. For example, we want true to become true. Certainly. We want false to become false. That sounds logical too. This last one, that false might become true, we've seen in our previous lecture that this is not actually what we mean. What we mean is that false, together with the context, is leading to true. Whatever's the premise in Q that's becoming true, that had to be entailed by something in the story. And that's either in the premise itself, at which point we get true implies true, or it's somewhere hiding in the context. That simplification devoid of context can look like a fallacy. It can look like a weird thing to say is logical. So always remember, there's always a context somewhere. You're just simply, in classical logic, choosing to ignore where things come from. If we write this down, we can use symbols only. And we can see that we replace true with a capital T and false with an upside down T. So true together with true leads to true. True together with false, that won't be allowed. That's the one to avoid. False at the beginning can match anything, so both of those are allowed. This is why there's only one rule to remember, that true, false is not an implication. So in summary, the classical if-then-else is sometimes taught purely as this table, but keep in mind that implicit context is what's making this look so symbolic, or what people call formal. If you ever hear someone say formal in the regular speech, you might think that it means they wear a bow tie or something. What it means in mathematics and logic is that it follows a form or a formula. It's following the shape of the symbols. It's not putting any meaning to it. It's simply saying that when I see a T followed by a T, I get a T. It's the form of the logic without any meaning. So this is a formal implication simply because we've distilled everything out of meaning. We've simply said, what's the final result? It's classical judgment. So, in summary, there are two further types of implication. Our first implication is the weakest of all. You could have as many premises repeated in order as you need, but you might not get everything you want. So, we then need to add our conditions. If we want to count resources, moving to something like a linear logic, we will not add weakening and contraction. That will be the most specific form of implication. As we start to ignore the use of resources, we can move to an implication that's process-based, or what's known as intuitionistic logic. And here the typical trick is to add weakening and contraction rules, which allow you to reuse a premise or not reuse a premise as many times as you like. And then finally, it's the incidence implications, where all we care about is what happened, true and false. This is classical logic, and it ignores the reasons. Now you might say, why would we ever ignore the reasons? I want to give you one last parting reason to think classical is perhaps the most common. Imagine that you simply wake up every morning and you see the sun rise, and you haven't taken a class on astronomy and the solar system. You might deduce the implication that when it's morning, the sun will rise. That's a truth-based implication. That's an incidence-based implication. You don't have a way to explain it until you understand the solar system and the rotation of the planets. There are many things that when first encountered are simply evidence-based. They're just an incidence that happens concurrently, and they can lead to implications as our first path in understanding it. A deeper understanding, a scientific discovery, is to produce a process that could explain why one thing leads to another. And then we can move to an engineering component where we get down to the nuts and bolts of how exactly that process uses the resources available. That's the strongest form of implication. So in your thinking, remember that when you first encounter something in the sciences, it's likely to be this incidence-based classical logic that you need. Once you're taking a known classical logic and trying to put it into some reasoning, like making your first computer program, you'll move to the process-based implication. And once you get down to knowing how best to engineer it, that's when you move into other types of logic, such as um, linear logic and keeping track of parallel information. We have one thing left to discover. What happens with paraconsistent? What do we do when we have both true and false? That will finish our story on implications. Until next time.